Okay, great. It's always fun to see Salvatore do his tablet talk. It's kind of different, isn't it? Okay, next up, we're going to have our Redis Labs co-founder and CTO, Yiftach Shoolman. Please welcome Yiftach.
Hi, everyone. Thank you for coming. So the topic today will mix between operational stuff and developer stuff. So just out of my curiosity, how many of you here are pure developers that don't touch operational stuff? How many people are doing some operational stuff, server setup, HA, clustering? So, okay, good. I'll try to mix. Why we are here? So there is a pure single reason for that. You want to create application that will be instant. That means 100 milliseconds from the time you click the button until you get the response. 50% goes to the network, 50% goes inside the database, inside the data center. But if you look carefully, usually for every user transaction, you have multiple interactions between the application server and the database. And in order to confirm the 100 millisecond end-to-end response time, your database needs to respond in no time, under 1 millisecond. And we all know that there is only one solution in the market that does it. It's called Redis. So this is why we're here. Interesting observation. We are trying to build Redis for the next generation of the use cases. And this is taking from a well-known website called DB Engines that compares between multiple databases. I guess most of you know Redis is, of course, one of the top 10 databases here. But what is very interesting in this chart, it shows you which data models people now are using when they design new applications. So the top one, in terms of increasing popularities, are TimeSeries, graph, search, Redis with key value and data structure, and of course, documents. The last one is relational. So if you're thinking about new application and you stick to relational word, you probably do something wrong. Now let's try to answer several questions. Is Redis reliable? Can I use it more than a cache? It's a good question, and let me first share with you the experience that we have with Redis Enterprise, and then we'll show you a few tricks how we made Redis a real database. So first of all, we are over 6 years in production, one of the first company on earth that did database as a service in the cloud when the cloud was completely unstable. We manage over 1 million databases, over 500 data centers, on-prem and cloud. And since we started, we had over 3,000 node failure events and over 100 complete data center outages. This is huge. And for those who enabled all the HA features, we don't know about any data loss. Now let me share with you a few tricks that we did. But before that, let's go over the basic ingredient of a reliable database. So you need to have HA and failover, preferably fast failover, data persistent backup, and hopefully active, and disaster recovery capabilities. I won't cover everything, but I will cover a few important ones. HA. So one of our HA concepts is to do pure in-memory replication. So if you look at the default configuration of Redis, usually when you start the replication, it first writes to disk at the master, move from the disk of the master to the disk of the replica, and then load to the replica. But we also developed what we call diskless replication with Redis. That means the master can directly write, but to the storage of the replicas. There is a reason why we did it in the open source, or why Salvatore decided to do that in the open source, because if you have failure of master and replica simultaneously and you don't do that, you can probably lose data in some situations. So in the Redis Enterprise, we have a layers that overcome this, and we managed to do everything in one single operation between the master and the slave. This is something like 2-time improvement of the replications. Another interesting concept that I would like to share with the operational guys is where do you put the watchdogs of your database cluster. Watchdogs, I mean the ones that monitor your database, monitor the nodes, and decide if the node fails or not. You can look at it like the Kubernetes management system, or if you deploy Redis with Sentinel outside the cluster. So in the left side, this is where the approach is to put the watchdogs outside the cluster. And in the right side, this is the approach of putting the watchdogs inside the cluster. The Redis open source and the Redis Enterprise use this approach from the right. And let me show you what will happen when you have a network split event. Let's assume the master is now disconnected from the two slaves. On the left side, for some reason, this network split included the watchdogs and not your application server. So there is a problem because these watchdogs cannot tell the cluster to fail over. On the right side, there is the same network split, but the watchdogs are part of the cluster, and they can react. So practically what will be the end result is on the left side, your application cannot connect to the cluster. On the right side, a failover will happen, and this node that used to be the master will now be taken out of the cluster, and a failover will happen. So this is just explains you why you need to have the watchdogs inside the cluster for any database. And if you work with Kubernetes, there are practically two levels of watchdogs. One monitors the cluster operations, and one monitors the entire operation of your infrastructure, the node setup, et cetera, et cetera. Another interesting approach that we have is how to deploy a cluster in multiple AZ, or multiple racks configuration. So I would like to share with you a few things that you should take into account. First of all, you cannot do it with two AZ. Many times people are asking us, let's deploy multi-AZ or multi-rack configuration with just two, because this is what we have in the data center. Okay, but what happens if you have a network split? You have a split brain decision. You need to decide who is active and who is not active. So you must have at least 3 AZ. And by the way, if you know the history of the clouds, many of them started region with just 2 AZ. So practically, you could not deploy any distributed databases on these configurations. Now it's over. Most of them have more than 2, at least 3 or 5 AZ, and this is at least the first requirement. Second, your master and your replica should, of course, live in different availability zones, because if something fails, you need to survive the failure. Third, you need to make sure that the distance between the AZ is less than 10 milliseconds. Why it is important? Because if it is not like this, all of a sudden you will see some network glitch, and you will see some cluster problems. You will think that the nodes are not connected because there is an issue, but there is no issue. It's just network delays. So they should be close to each other. Otherwise, it is very hard to operate the cluster. And of course, you need, this is the fourth one, you need to make sure that there is no situation where the majority of the nodes of the cluster are living in one AZ, because when it fails, you want the cluster to continue operating. After sharing with you what we did internally, just part, I would like to share with you the benchmarks that we did in which we compare how vendors of Redis survive a failover event. And we compare, of course, Redis Enterprise by Redis Labs to AWS Elastic Cache, to Heroku Redis, to Compose from IBM, and to Azure Cache. As you can see, the bars tells you how long it takes to failover, and the line shows you how many of the failover ended with losing data. Okay? I think this speaks to itself. I don't need to tell you more than that. Let's move to the next topic. Active-active. Very important for reliable database. Why do you need active-active? I think for Redis, it's clear that the first probably use case is session management. You go by train from San Francisco to the Silicon Valley. You do shopping. All of a sudden, your DNS switch you from one data center to another data center. You don't want to make your cart empty. Yeah? So this is just one use case. Another use case is to make sure that you're ready for disaster recovery. You want to work in a situation where a few of your data centers are down, and you continue working. What's interesting in these two use cases is that you usually don't write simultaneously to the same data center. You have a way to do DR or switch over, but you don't read and write from the same to different data center at the same time. You read, but you don't write. So this is why active-active is important. It allows you to build an application that reads and writes from different data center to the same data set simultaneously. Okay, this is the third use case. And there are many approaches to solve this problem. The Cassandra approach, which eventual consistency, you need to have a protocol between the replica in order to get to an agreement. So if the distance between the data center is like 100 milliseconds, the client needs to wait after each write. The same goes with Spanner from Google, and which is a completely consistent distributed database. You need to wait sometimes 200 milliseconds for every write. This is something that cannot work with Redis. Also, conflict resolution is a very hard problem to solve. You don't want to solve it at the application. And you don't want to use something that's called last write win, sorry. LWW, last write win. Because with Redis, when you have a very long list or a very long sorted set, you don't want that someone that was not connected to you all of a sudden will erase it because it was the last one who wrote to that. Okay, so it doesn't work in this configuration. This is why we invented the Redis CRDT. So Redis CRDT was not invented by us. CRDT was invented by a group of 10 professors 10 years ago that came to solve the problem of Google Doc. When they start to share something, you write something, someone else is writing, and then there is a problem of conflict. And this is where CRDT invented. We took the lead researchers there, Professor Carlo Baquero, and he helped us to do CRDT over Redis. Some people call it CRDB, but it's the same mechanism. Eventually, what it allows you to write to Redis like if it were a local Redis. And behind the scene, without any protocol between the replicas, everything will be converged to the same values. How it works, I won't explain everything because everything works per data structure of Redis, and it's a bit complex and we don't have enough time. But this is a proven technology that works in the field, transparent to the way Redis works. So if I want to summarize it, if you want to use active-active solution, you can either use Cassandra or DynamoDB approach and wait 100 milliseconds for every write, or Spanner 200 milliseconds for every write, or you should use Redis CRDT, which has this strong eventual consistency and casual consistency. I won't explain what it means, all this, but eventually it allows you to feel like it's strong consistency with 1 millisecond latency. Now, after we did that, we said, okay, we have multiple availabilities mechanism. Why shouldn't we give our user to enjoy from that? And about 6 months ago, we announced 5 nines availability for our cloud service. And if we don't meet this, this means something like 26.3 second downtime a month, we credit you, okay? So this covers the first part of my presentation. I'm a bit out of time, so let's move to the next one. The next one, I would like to ask, how fast do you think Redis can go? Before I ask that, let me explain you how do you make Redis runs faster. So first of all, you need to make sure, like Salvatore mentioned earlier, that the application can directly connect to Redis without any other network ops. So the clients should be smart, should know where every key lives, and send a single request in order to get this key without, doing manipulation over the network. Second, you would like to build an architecture that utilizes all the core of the system. This is, of course. And third, you would like to make your cluster as share nothing as possible. So ideally, you don't want the shards to know each other because they don't need to deal with cluster management, failover stuff. They can only need to deal with serving the data. Let's do the control plan by someone else. With the Redis Enterprise, we also implemented proxy that sits before the shards, okay? From the point of view of the client, it's like a big shard that runs across multiple hash slot. But practically, there are multiple Redis processes behind it. This proxy can also accelerate Redis because it opens persistent connection with each Redis it manages, and practically pipeline the request to a very few connections. So it's avoid connection setup and tear down. And when you pipeline requests to Redis, you can accelerate the Redis operation significantly. So this is how it looks. And this is what we did a year ago. At RedisConf 18, we managed to run 50 million ops per second over just 26 servers. This is nice, but we didn't stop there. During the last years, we did several things. We first improved the core of Redis. There are multiple improvements of Redis 5.0, especially for big pipeline. We improved the core of the Redis Enterprise, the way the proxy speaks with the shards. AWS improves their infrastructure. They now have 72 vCore running on 3.5 gigahertz. And we also played with NUMA setting. So to show you the new benchmarks that we did, the new benchmark result, I would like to call to the stage Mikel and Yael from Redis Labs to explain what they did.
Thanks a lot, Yiftach. Thank you, Yiftach. Well, hi everyone. My name is Niall, and we did the benchmarking of the latest Redis Enterprise release. First of all, I want to mention that the Redis Enterprise has close to linear scalability, and I would like to show you what we can do on the single node first, right? Maintaining the latency under 1 millisecond and using the get-set ratio 1:1, pipeline 9, and the key size value just 100 bytes. On the single node, we can do with the 4 shards 2.9 million separation per second. 6 shards, almost 3.9 millions, and 8 shards, 4.2 millions. This is impressive result, actually, but the system is loaded only at 50%. Okay? But when we try to increase and put more shards on the single instance, we can get better throughput with the default configuration. There are context switches on the proxy, on the Redis shards, and also Redis shards are moving between the NUMA nodes on the same machine, and it's like the throughput overall is unstable. So later we tried to do some tuning for the NUMA, for proxy and the Redis. And using exactly the same configuration, just 8 shards, we can do 4.8 already, and 10 shards, 5.3. Okay, what is NUMA tuning? This is basically balancing of the proxy threads between the NUMA nodes, between the CPU sockets, right? And binding CPU and the memory of the Redis process to a specific NUMA node. This is it. Okay, we are ready to scale now, and I will show you a short video demonstration. This is the example for 10 nodes. We can do 50 millions now, just with 10 nodes. 20 nodes, 100 millions. And next one, and the final, is 40 nodes. With 40 nodes and 400 shards, we can do 200 million separation per second, maintaining the latency under 1 millisecond. Thank you.
So as Neil explained before, on one node we was able to achieve 5.3 million operations per second. And on the 10 nodes, we wanted to match the results from last year, and we was able to achieve 52 million operations per second. Then we scale out, and on 20 nodes, we was able to achieve 100 million operations per second, and we stopped at 200 million operations per second on 40 nodes. But let's see to have next year. So with our shared nothing infrastructure, we was able to have more than 500 operations per 1,000 operations per second per shard, and more than 5 million operations per second per node in our cluster. In this case, we was close to optimal linear scalability of 94%, which is actually 6% performance decline between one node cluster and 40 node cluster. So I was really amazed with all performance improvements and that we break our own record with time compared to the last year RedisConf, and we improved our performance from 50 million operations per second to 200 million operations per second, which is 4 times performance improvements, 2.6 times performance improvements per node, and 5 times improvements per shard. This kind of experiments show us that based on the proper infrastructure and architecture, like Redis Enterprise, that Redis can beat any record on infrastructure with less amount of nodes than any other database.
Thank you very much. Very, very, very impressive answer. Now, of course, the question to be asked is it affordable? Because you run in memory, it's costly, yeah? So why should I even start developing something with Redis where tomorrow my ops guy will tell you I will not deploy it because it costs too much money? And this is what we started to see a few years ago, that our customers are looking to move the data set from Redis from typical a few gigabytes to hundreds of gigabytes to terabyte, and today with petabyte volume. So running something in memory is fast, but it's also expensive. So if we take just this example of AWS, if you pay just 15% more, you can practically use the same amount of memory with five times more virtual memory that runs on the SSD and use the Redis on flash technology. So this is not running as fast as Redis in terms of throughput. It keeps the same sub-millisecond latency, but instead of around 1 million ops per second per node, we saw that we can reach more. It operates with something like 100,000 ops per second and still under sub-millisecond latency. Why it is important? Because let's assume that you have this use case with 1 terabyte, with replication 2 terabyte, and 100 ops per second throughput. Here are the alternatives that you have in the market. You can go to AWS Elasticache and pay something like $720,000 a year reserved instances. You can go and do it yourself with Redis infrastructure. It will cost you $500,000. Or you can go to other NoSQL database. It will cost you less, but the latency will be around 10 milliseconds. Or you can use Redis on Flash with just a fraction of the cost, $140,000 a year, and just keep the latency sub-millisecond. And again, we didn't stop here, because there are people who still want not to pay too much, but they want the throughput close to RAM as much as they can. And luckily, Intel has been working for the last 5 or 7 years on technology called persistent memory. I don't know if you heard about it. It was called 3D Crosspoint. It's practically take SSD and RAM technology, put it in a chip, and deliver it as a DRAM form factor. So on a single server, you can now host 3 tera and even 7 tera of persistent memory combined with DRAM. And what's interesting about this technology is that in some server setup, it runs very, very close to DRAM. Almost no differences in terms of performance. And of course, much, much cheaper. So if you decide to go with Redis, there are solutions that allow you to deploy Redis in a cost-effective manner like any other disk-based database. Very close. My last paragraph is what else you can do with Redis. So the first thing I would like to discuss is Redis and TimeSeries. TimeSeries has been a very popular use case for Redis for a while. You can use it by 2 techniques, practically. People are using it with sorted set and hashes. So everything is inside the sorted set. The score itself is the time that the event happened, and you can point to an hash if you want to detail the event. Or you can use it with the new streams capabilities. But as I mentioned earlier, TimeSeries is today one of the most popular, I would say, trends in the database space, and you need to do a lot more than what these 2 techniques provide. So for instance, you need to do downsampling. You need to do some aggregation. You need to do some labeling. Of course, retention rule. You want to do some enhanced queries. You want to connect to standard device to monitor your tools. And we want to do compression like delta encoding in order to keep more in the same infrastructure. So today we would like to announce the general availability of Redis TimeSeries. Redis TimeSeries is a modules. We announced it at RedisConf 19. We ran for a few months in a beta period, and we think that the product is now available for GA. It provides all the capabilities that I mentioned earlier. We still don't provide the delta encoding compression, but it will become soon available. Just a few notes how it was built. It was built on the same Radix tree architecture of Redis tree. So it's supposed to be very, very fast. And this is what I'm going to show you in the next benchmark. So we did a benchmark that compares sorted set in two ways of form factors, Redis TimeSeries and Redis streams. We did free test. We tested, how fast is data ingest, which is extremely important for TimeSeries. As you can see, in this case, one of the sorted set configuration was faster than anything else by 3 times. But look at the number. This is a single instance, yeah? So sorted set, we were able to do 30 million, and TimeSeries, we managed to do 11 million, and stream, we did something like 10 million, which is huge for a single instance. On the other hand, when we started to query the database, we found out that with the new capability of the TimeSeries, we can practically do 100 times faster than existing capability with Redis, and without developing any Lua style of code in order to do all the aggregation and stuff like this. And the last thing that we tested is how much memory usage you can do. And again, TimeSeries is in between the sorted set and the stream, mainly because compression is still not there. But with all these features that we added, we think that it runs as fast as Redis. And one of the important things that we did, and you saw this in the benchmark examples, that it works seamlessly with Grafana. So by the way, Redis Enterprise, the entire metrics about the databases that you provide are running on the top of Redis TimeSeries in production for a while, and you can connect Grafana with Prometheus and just monitor everything. This is TimeSeries. Another thing that I would like to mention is how Redis works with AI. So we did a lot of experiment about how to deploy AI with Redis. We had Redis TensorFlow, we had Redis ML, we also have Neural Redis. All of them were a kind of experiment to see where Redis can fit in the AI world. And eventually, we decided to design, together with a company called TensorWork, a Redis AI module. The Redis AI modules practically works with a new type of data types. It's called tensors, and it supports 3 types of machine learning. Sorry, 2 types of deep learning and 1 type of machine learning. So PyTorch, TensorFlow for deep learning, and Onyx for machine learning. It can run on a CPU or a GPU. It supports Torch script, so you can do something like Lua in the kind of Redis for the AI modules. And of course, it's scale and highly available when you run it with Redis. So the whole idea here with Redis AI is not to have another way to train your model, but to have another way to serve your model. You can practically create a model in TensorFlow and serve it in PyTorch. You can actually create a model and upgrade while running your machine learning in production without no downtime. And you can scale it either by adding shards or CPU. And what is else interesting here is that you can run your AI very close to the data. And why it is important? Let me give you an example of transaction scoring use case. Transaction scoring is a well-known use case for all the card issuers. Yeah? You sweep your card, someone needs to approve your transaction. During this process, usually what happens, the application go to the database and take the profile. They take the profile of the merchant, they take the profile of the user, they take the profile of the devices in which you did the transactions, and then they vectorize it and send it to AI to decide whether this transaction pass or fail. This is nice, it works, but it's slow because there are a lot of interaction between your application server, the database, and the AI server. Now, think about a situation where everything is deployed in Redis with Redis AI. With a single API call, everything that I discussed earlier is done by Redis. And you can do, like I mentioned at the beginning, under sub-millisecond latency, an operation with AI. This is why when you deploy AI in production, think where your data is. You can have much better performance if they are merged together. My last topic is about Redis and other data models. And again, let me return again to the figure I showed you initially about the 5 popular data models that today are running in databases. We think practically there are 7. We need to add AI and stream. This is not only the 5 that DB Engine shows. And the challenge, of course, is how you can run the new Redis with all these modules and maintain sub-millisecond latency. And in many of your next-generation application transactions, you will combine between a use case. It won't be just a single use case. For that, we created 3 technologies that I would like to share with you. First of all, we call it direct intermodule communication. That means modules can find other modules that are deployed on Redis and use them. For instance, Redis Graph can use now Redis Search in order to better do graph traversal. The other technology is what we call single dataset copy. When we deploy a module on Redis, we can use existing data structure of Redis in order to operate. We don't need to create a new type of data. We can create just an index to the data. These techniques allow us to use the ingredients that we have with Redis Enterprise already. So for instance, by just deploying Redis Search, we can run search on active-active topology because it uses the existing data types of Redis without inventing a new data types in order to operate. Of course, it has its own data types, the search, but it builds it from the internal of Redis. And the last, and probably the most interesting one, is what we call Redis Gear. Redis Gear is a new serverless infrastructure that allows you to program intermodule operation inside Redis. This is the architecture of Redis Gear. It's built on a C-based infrastructure, and it supports any language with C API. So now you can run gears with Python, but very soon Java and Scala. And it has these 3 components like map reducer, coordinators, and gear executors in order to run the gear inside your Redis. Let me give you just an example. Let's assume that you want to create a gears. You would like to create an application that counts how many messages arrive to your stream in a TimeSeries database. So you create these gears. These are just 3 lines of code. You just first create the pipe. I mean, you prepare for the operation. And then for every message that arrives, you just increment the time series. And you associate this to a specific stream that you want to count. This sounds like science fiction, so I would like to give you one last example how it works in production. So we have this company that does robotics arms. And they have the challenge, they want to automatically control this arm in factory operations. And it has a lot of sensor and information, et cetera, et cetera. Usually it delivers something like 1,000 messages a second. And these messages are delivered to streams. And this guy created a gear that takes the messages from stream and put it in time series in order to filter the messages. After they filter the messages, they send these messages to Redis AI using TensorFlow in order to generate commands to the robotic arms. These commands were stored in the streams, and then the robotics arms read them and do operation, like ripping the box, moving the arm, et cetera, et cetera. What's nice about this? Everything ran on a single Redis instance, what we call Redis Edge. I think it is a wonderful use case for gears. I hope you also. So to recap, we talked about Redis reliability. We showed why 5 nines availability is important to operate Redis. We show how Redis can scale to 200 million ops per second with just 40 nodes, and why you can run Redis on practically disk-based hardware without the cost associated with RAM. And then last, we showed you how you can do multi-model operations in Redis, and you can run it on the edge, on the cloud, or on-prem. Thank you very much.
Thank you, Yiftach. Okay, before we go to break, I just have a couple quick announcements to share with you. First of all, I thought it was great that you said it seems like science fiction, because you remember the black monolith from 2001, A Space Odyssey? You guys remember that? To me, that feels like a great way to describe Redis sometimes, because there's all these 10 different data structures in open source Redis, and once you realize that, you can stare into it and see the magic and the science fiction. But if you want to learn more about Redis, there's the 10 data structures, there's so much more, there's the modules. If you want to make your science fiction reality, we have some great opportunities for you to learn more. Okay, hold on. This is going to move, right? There we go. All right, so we have Red workshops. The next one that's coming to the East Coast is coming to DC. So take a look at that, July 11th. And we have others that are coming around the US and then soon the world. So keep an eye out for the Red workshops. These are one-day events where you will get some training and other education all around Redis. We also have our Redis University, which we are rolling out more and more courses every month. We have some courses that are coming up soon or have just started. By the way, if they've just started, you can still join, but there's some other ones coming up in the next couple months. So check out Redis University. And we are very, very close to nailing down the date for RedisConf 20, which will be in San Francisco in May. And this is always a fun event with people from all over the world coming together, and we have many, many tracks and many, many topics. So put that on your calendar too if you want to really feel the vibe. So with that, we're going to go ahead and break. But when we come back, we have 12 more talks. 10 of them are from the community members. So take a break, and we'll see you back in 15 minutes.